Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome our members to the group and I kindly like to request our members to subscribe, engage us in the comment section and also ring that notification bell to be getting updates on our various discussion in mathematics and sciences. Now in this specific case, we're going to look at the concept of electric potential, and this is going to be a culmination of various discussion we have had on the concept of electric charge, electric field, and of course the concept of the electric field lines. We are going to see the interaction of an electric charge and of course this is specific aspect of an electric field, and try to see what are some of the quantities which we are going to derive from there. Now one of those quantities is electric potential, and of course we're going to consider a test charge that we can give in terms of let's consider a test charge which we can give in terms of a Q naught. And if this test charge is placed in an, of course, electric field which has been created by another object, which we can just give in terms of an electric field created by another object given as this is specific vector quantity, we're going to see that there's going to be an electric force that is going to act on this specific object, which is basically going to be a conservative force. Now in this case, we can give this specific force as a product of this specific charge and the electric field. And therefore, this one can be given in terms of a Q naught and this particular electric field given as such. So I'm going to give this one as an initial, basically give it in this specific format. So we're going to have this force being created due to the interaction of this test charge placed in an electric field created by another object. Therefore, we're going to have this specific magnitude of force represented that using this specific formula. Now, I've mentioned that this basically is going to be a conservative force, which means it's going to be, of course, going to be considered as I'm going to mention later, whereby either the charge is going to be independent of another aspect, as I'm going to elaborate later in this specific discussion. So when this test charge is moved in this particular field by an external agent, there's going to be some work which is going to be done by the field on this particular charge, which is going to be equivalent to the negative work done by the external agent that is going to cause this specific displacement in this particular field. Now, in this, for us to understand this, we're going to consider a slight motion or an infinitesimal displacement in this specific field. Oops, I can just give this one more legible way. So I've said that if we consider this specific particle which is being moved in this field by, of course, or if the test charge is going to be moved in this field by some external agent, there's going to be some work which is going to be done by the field on this charge, which is equal to the negative work done by the external agent in causing this specific displacement. And of course, we are going to consider an infinitesimal, which is a small displacement. We are going to consider an infinitesimal displacement in this specific field in terms of ds. So basically from classical mechanics, or from the last discussion we had, s is going to be a displacement. So an infinitesimal displacement is going to be given by this ds, and therefore the work that is going to be done by the field due to this small displacement can be indicated using the product of the force and this specific displacement. Now we can define work as a product of force times displacement, and therefore this is going to be given, or rather we can just give this one in terms of the force. This is going to be just give it as such. So we're going to have this one as a product of the charge as we have given. So let's consider this one as our equation 1. So from equation 1 we can substitute our force to be equivalent to the product of the charge and an electric field given as such, and this is going to be multiplied with a displacement which is an infinitesimal displacement given as such. Therefore we are going to see that as the work which is going to be done by this field given as such, the potential of this charge and the field system is going to be decreased by a specific amount. Now we can represent this specific potential which is decreased in a specific amount using du. And of course, this is going to be a specific amount of potential which is going to be, of course, decreased using that specific amount. And this is going to be the change in potential equivalent to the work negative the work done. And therefore, we're going to have this one given as the product of this specific field and E, which is the force we have said times the small displacement which we have given in terms of ds. So therefore, this is going to be equivalent to the negative the work done by this specific displacement which we have given on the work done, which is going to be the work done by this specific field given in terms of du, equivalent to that specific equation. So we're going to have this one as our equation 2 for reference, and then we shall have this one as our equation 3 for reference respectively. Now we're going to see that it is going to be a small change in potential energy. Now for an infinitesimal displacement of this specific charge, and we're going to consider perhaps from a point A to B. So this is going to be a displacement from a point A to B of this specific charge. Let's give it as a Q naught for that small illustration. The change in a potential energy can be given in terms of those specific illustration for A and B, whereby we're going to have it as delta U. So therefore, this is going to be the change in potential energy from A to B, given as U sub B, U sub A given as such. And that is going to form a fourth expression for that one, implying the change in potential energy. Now, this one can be given in terms of an integration, which is going to be given in terms of the negative integral of Q. And of course, we're going to have this one from A to B of this specific product of E dot ds given as such. So we're going to have the integration of this specific change in potential energy given in this specific term. But as we're going to see, the charge is going to remain constant. Therefore, we're going to have the negative value over Q naught A from A to B over E to ds representing the delta U given as such. And that's going to form a change in potential energy given as such. So we're going to perform an integration as it can be seen from this specific sense. And as I said earlier, of course, we're going to see that this specific integral is going to be given a term which is the path stroke line integral, which is going to be independent of the path taken by the force which has been given in terms of F is equivalent to Q naught E given as such. As we had mentioned earlier, this specific force is going to be a conservative one. Now, the potential energy which we are going to be realizing from this specific case per unit charges can be given in terms of course, U over Q naught. So this is going to be the potential energy, which is going to be a potential energy per unit charge from this specific point can be given in terms of U over Q naught. And therefore, we can illustrate this one, of course, as U over Q naught, which is going to be independent of the charge. And it's going to have a specific value at every point in this specific field, which is going to be an electric field under consideration. Now, this specific quantity, which we have given in terms of a ratio of U over Q, is referred to as the concept of, or rather the electric potential. Now, in this particular case, we can see a culmination of this specific aspect from the force and considering an infinitesimal displacement and the concept of a work done, which is equivalent to force times the distance. And therefore, if we consider this is going to cause a change in a potential, of course, the energy, which is going to be given in terms of these specific values of course, the change in the potential energy given in terms of work given as such. And we have considered the case from A to B, which is our displacement, and therefore, the change in potential energy can be given as an integral form of this specific aspect of a change in potential. Now, the ratio between the change in potential and this specific, of course, charge which we have given as a Q naught is going to be giving us an aspect of the concept of the electric potential. Now, we are going to initialize this one using V, which is going to imply our electric potential in this specific system under consideration. Now, if you try to look at this specific aspect, then therefore we're going to come up with another equation 5, which is going to be giving us our electric potential equivalent to the ratio between this specific charge and the potential energy given as such. And this is going to form our equation 5 given using that specific formula. Now, the electric potential, which is going to be the work done per unit charge, of course, can be given using the standard units, and these are going to be given in terms of joules per Coulomb. perhaps because of the space. But the dimension for this one is joules, joules in terms of energy, and then the charge is going to be given in terms of a Coulomb. So we are going to come across these specific units as we're going to go by, and sometimes this is going to be given in terms of volts. Now in this case, 1 volt is equivalent to 1 joule per Coulomb. And this is going to be a conversion which we are going to come across later in case we find an evaluation which requires us to find, of course, this specific quantity in a particular dimension. So in this case, the potential difference, as we have said, which is the difference between A and B, can be given as well in terms of the delta V, which is equivalent to VB minus VA, given as such. So this is going to be also another consideration which is we're going to consider. In an electric field, it's going to be defined as a potential energy of the system by the test charge Q, which we have listed above. Now this apart from other aspects which we're going to consider for the electric potential, are going to assist us in trying to define perhaps the potential or the electric potential of an arbitrary point of an electric field, which is going to be done perhaps from for moving a particle from infinity to a particular point, and that's going to give us a different aspect of this, a specific aspect of our potential energy. Now, before we close, I'm going to mention about a unit that is commonly used, referred to as an electron volt. And of course, this specific aspect of an electron volt is the energy, which of course is the energy an electron or a proton loses when it's moving through a potential difference of 1 volt. I'm going to elaborate it more as we come across it in our various applications, but I'm going to just give it as one quantity for the sake of evaluation. So 1 electron volt is the same as 10 negative 19 coulombs. So kindly check out description boxes for various links of other videos, and check a link which I'm going to put there, and subscribe for more details on science and mathematics. So that is it for now, guys. By God, please, we'll catch us in our next video.